Welcome to G Fun Facts Online. When we gaze through a telescope at the night sky, few sights are as universally breathtaking as the golden, banded sphere of Saturn suspended within its shimmering, icy halo. For centuries, this spectacular ring system has been the defining feature of our solar system's second-largest planet, earning it the well-deserved moniker Lord of the Rings. Yet, beneath this serene and majestic astronomical portrait lies a hidden history characterized by intense gravitational warfare, catastrophic destruction, and incredibly complex orbital dynamics. Saturn is not just a passive gas giant simply floating in the outer solar system. It is a highly dynamic, evolving world whose iconic rings and unusual planetary tilt are actually the physical scars of an ancient, violent cosmic event. To truly understand Saturn, we have to peel back the layers of its modern appearance and delve deeply into the delicate interplay of gravity, orbital resonances, and the tragic fate of a lost ancient moon named Chrysalis. The story of Saturn's orbital dynamics and ring formation is essentially a grand celestial detective story. It is a narrative that forces us to completely abandon the old idea of a static, unchanging solar system and instead embrace a cosmos where even the most massive, dominant planets are subject to chaotic, transformative forces. Let us begin with the enigma of the slanted giant. A planet's axis of rotation is rarely perfectly perpendicular to its orbital plane. Earth, for example, boasts an axial tilt, known scientifically as obliquity, of 23.5 degrees. This is a quirk of celestial mechanics that blesses our world with the changing seasons we experience throughout the year. Saturn similarly spins at a pronounced angle, boasting an even steeper axial tilt of 26.7 degrees. For a rocky, terrestrial planet like Earth or Mars, a tilted axis is relatively easy to explain by looking back at the violent conditions of the early solar system. During the chaotic protoplanetary disk phase, massive planetesimals routinely smashed into one another. A colossal impact from a Mars-sized object was more than enough to knock a rocky world completely off its vertical axis. However, applying this same violent impact model to a gas giant like Saturn presents a monumental physics problem. Gas giants are incredibly massive. To put it in perspective, Saturn is 95 times more massive than Earth, and because of this immense size, it possesses enormous angular momentum. To permanently tilt a planet composed almost entirely of hydrogen and helium, an impactor would have to be unfathomably massive. Even then, the fluid dynamics of a gas giant would likely just absorb the blow without permanently altering the planet's rotation to such a steep degree. As Jack Wisdom, a professor of planetary science at the Massachusetts Institute of Technology, notes, the tilt is simply too large to be a result of known formation processes in a protoplanetary disk or from later, large collisions. So if a giant impact did not knock Saturn over, what exactly did? For decades, astronomers theorized that the answer lay not in a sudden, violent collision, but rather in a slow, invisible gravitational tether to the outermost ice giant of our solar system, Neptune. Planets actually wobble as they spin, much like a child's spinning top that begins to slow down. This wobbling motion is known as axial precession. In the early 2000s, astrophysicists recognized that the rate at which Saturn's axis precesses was remarkably close to the orbital precession rate of Neptune. This cosmic alignment strongly suggested that the two giant planets were locked in what is called a spin-orbit resonance. Essentially, the theory was that the gravitational influence of Neptune, acting over billions and billions of years, had reached across the vast, dark expanse of the outer solar system to grab hold of Saturn, gradually pulling its axis into that steep 26.7-degree tilt. For a time, this theory satisfied the astronomical community. It was an elegant, mathematical explanation for a physical anomaly. But the universe is rarely so simple, and the arrival of NASA's Cassini spacecraft would soon unravel this neat hypothesis, revealing a far more intricate and dynamic reality. When the Cassini-Huygens mission arrived at Saturn in 2004, it commenced a 13-year masterclass in planetary science. Cassini was a marvel of human engineering. It mapped the planet's swirling cloud tops, plunged fearlessly through the icy, geyser-like plumes of the Moon Enceladus, dropped a specialized probe directly onto the mysterious, methane-soaked surface of Titan, and stared deeply into the complex, mesmerizing structure of the rings. But some of the mission's most vital, game-changing data came during its grand finale in 2017. Running low on fuel and wanting to protect the pristine moons from potential contamination, Cassini was instructed to execute a series of daring, suicidal dives right between Saturn's upper atmosphere and its innermost rings. During these final, thrilling orbits, Cassini precisely measured Saturn's gravitational field, allowing scientists back on Earth to map the distribution of mass deep within the planet's hidden interior. By understanding the planet's moment of inertia, which is how its mass is distributed from its dense, rocky core all the way out to its wispy outer atmosphere, researchers could definitively calculate the precise mechanics of its spin and precession. When Jack Wisdom and his colleagues at MIT fed Cassini's highly accurate, newly acquired gravitational data into their complex orbital models, the results were absolutely shocking. The math simply did not add up. The data revealed that while Saturn's precession is extremely close to being in resonance with Neptune, it is actually just outside of it. Saturn was not currently locked in a gravitational dance with Neptune at all. Somehow, it had escaped. But how does a planet the immense size of Saturn simply break free from a multi-billion-year gravitational lock? The answer lay in the behavior of Saturn's extensive, diverse retinue of moons. Saturn hosts a staggering collection of natural satellites, with over 140 recognized moons ranging from tiny, icy moonlets embedded deep within the rings to colossal worlds larger than the planet Mercury. The undisputed king of this satellite system is Titan. Titan is a true behemoth, possessing a remarkably thick nitrogen atmosphere and surface lakes of liquid hydrocarbons. Because of its sheer size, Titan's gravitational presence heavily dominates the entire Saturnian system. Cassini's precise astrometric measurements revealed a startling fact about Titan. It is actually migrating away from Saturn at a rapid clip of about 11 centimeters, or roughly 4.3 inches per year. While this may sound minuscule on a human scale, on a cosmic scale and over millions of years, it represents a massive, planetary shifting change in orbital energy. As Titan slowly spiraled outward into space, its gravitational influence on Saturn and the other moons shifted dramatically. This rapid outward migration provided scientists with the gravitational lever needed to explain Saturn's initial tilt. As Titan moved outward, it helped push Saturn into that initial resonance with Neptune. But Titan alone could not explain how Saturn eventually broke out of that resonance to reach its current, slightly decoupled state. To balance the intricate mathematical equations of the solar system, the MIT team realized that a massive, missing piece of the puzzle had to exist. Saturn must have once had another moon. To solve the dual mysteries of Saturn's current axial tilt and its narrow, puzzling escape from Neptune's gravitational grip, Jack Wisdom and his team proposed a meticulously tested hypothesis in 2022. They proposed that the Saturnian system was once home to an additional, massive moon. They named this lost world Chrysalis. Calculations suggest that Chrysalis was roughly the size of Iapetus, Saturn's third largest moon, which measures about 1,500 kilometers, or roughly 900 miles, in diameter. To picture that, it is about half the size of Earth's own moon. For billions of years, Chrysalis was a stable, harmonious member of Saturn's lunar family. Together with Titan, Iapetus, and the rest of the icy satellites, Chrysalis orchestrated a collective gravitational pull that kept Saturn's wobble perfectly synchronized with Neptune. However, the solar system is a giant clockwork mechanism where the gears are constantly shifting. As Titan continued its relentless, creeping outward migration, the delicate gravitational harmony of the Saturnian system began to deeply fracture. Between 100 and 200 million years ago, which is a time when dinosaurs like the Stegosaurus and Allosaurus roamed the Earth during the Jurassic period, the expanding orbit of Titan pushed Chrysalis into what astronomers call a chaotic orbital zone. Suddenly, the once stable moon found itself subjected to extreme, unpredictable gravitational perturbations. It began to experience a series of dangerous, terrifyingly close encounters with both Titan and Iapetus. These gravitational near misses violently warped Chrysalis' orbit, turning it from a neat circular path into a highly eccentric, elliptical plunge that brought it dangerously close to Saturn itself. Around 160 million years ago, the fatal moment finally arrived. Chrysalis swung too close to Saturn, breaching a terrifying invisible boundary known as the Roche limit. The Roche limit is the critical, mathematical distance at which the tidal forces exerted by a massive primary body, like the giant Saturn, exceed the internal gravitational forces holding a smaller secondary body, like a moon, together. As Chrysalis crossed this doomed threshold, the gravitational pull on the side of the moon facing Saturn became vastly stronger than the pull on its far side. The solid ice and rock of the moon began to stretch, groan, and aggressively fracture. In a cosmic blink of an eye, the immense, unstoppable tidal forces ripped Chrysalis entirely to shreds. The researchers conclude that approximately 99% of the shattered moon's mass was swallowed completely by Saturn's swirling, gaseous atmosphere. But it is the remaining 1% that changed the solar system forever. This fragmented debris, consisting mostly of incredibly pure water ice, remains suspended in orbit around the giant planet. Over millions of years, these icy fragments collided with one another, grinding down from the size of massive mountains to boulders, then to pebbles, and finally to microscopic dust, eventually spreading out to form the dazzling, expansive ring system we see today. The sudden, violent loss of Chrysalis was the precise event that allowed Saturn to snap out of its resonance with Neptune. As Burkhard Militzer, a UC Berkeley professor and co-author of the study, explained, when you lose an entire moon, you have one less handle to jerk Saturn around. By abruptly shedding this massive gravitational anchor, Saturn was left with its steep 26.7-degree tilt, serving as a permanent, slanted monument to the moon it destroyed. The Chrysalis hypothesis is widely celebrated within the scientific community because it acts as a grand unifying theory. It solves not just the mystery of Saturn's tilt, but also one of the most hotly debated topics in all of planetary science, which is the true age of Saturn's rings. Since Galileo Galilei first observed Saturn in 1610, initially mistaking its rings for ears or twin moons, and Christian Huygens correctly identifying them as a disk in 1655, astronomers have deeply wondered exactly how old the rings are. For a very long time, the prevailing wisdom was that the rings were primordial, meaning that they formed 4.5 billion years ago alongside Saturn itself, coalescing slowly from the leftover material in the early solar nebula. However, if the rings were truly 4.5 billion years old, they should look very, very different to our telescopes today. Space is incredibly dusty. Interplanetary micrometeoroids, carbon-rich dust, and the dark soot of ancient comets constantly drift through the vacuum of the solar system. If Saturn's rings had been exposed to this endless cosmic pollution for billions of years, they would have inevitably grown dark, dull, and soot-colored. Instead, the rings of Saturn are incredibly bright, highly reflective, and composed of 98 to 99% pure water ice. This pristine, sparkling composition strongly suggests they haven't been accumulating dust for very long at all. Once again, Cassini's grand finale provided the ultimate smoking gun. By flying daringly between the planet and the rings, Cassini directly measured the gravitational pull of the entire ring system, allowing scientists to calculate its total mass with unprecedented accuracy. The rings turned out to be surprisingly light. They contain a mass equivalent to about 40% of the mass of Saturn's tiny moon Mimas, or roughly 2/3 the mass of Earth's entire Antarctic ice sheet. In astrophysics, mass and age are deeply intertwined when it comes to ring systems. A massive, heavy ring system can absorb micrometeorite impacts and remain bright for a much longer period of time, while a low-mass ring system will darken much faster. Combining the incredibly low mass of the rings with the known rate of dust pollution in the Saturnian system, researchers arrived at a stunning, definitive conclusion. Saturn's rings are practically infants. They are only between 10 million and 100 million years old. This incredibly recent time frame aligns absolutely perfectly with the violent destruction of Chrysalis, roughly 160 million years ago. Just as an insect's chrysalis lies dormant before bursting forth to reveal a spectacular, beautiful butterfly, this lost moon orbited quietly for billions of years before its dramatic, explosive destruction birthed the most beautiful feature in the entire night sky. The sheer anatomy of this celestial masterpiece is mind-boggling. The debris of Chrysalis now forms an expansive, complex structure that stretches across hundreds of thousands of kilometers of empty space, yet is impossibly, almost unbelievably thin. In many places, the rings are only about 10 meters or 30 feet to 100 meters thick. To visualize this, if you were to scale Saturn down to the size of a standard basketball, its rings would be significantly thinner than a single human hair. The ring system is broadly divided into several main sections, labeled alphabetically in the order of their historical discovery. The most prominent and visible from Earth are the A, B, and C rings. The B ring is the brightest, the widest, and the most massive of all the rings. It contains the vast bulk of the ring system's icy material, and is so incredibly dense that it blocks almost all sunlight from passing through it. Then there is the A ring, separated from the B ring by a massive, seemingly dark gap. The A ring is slightly fainter but features incredible dynamic structures within it. This includes propeller-shaped disturbances that are constantly caused by unseen, house-sized moonlets embedded deep within the ice, carving through the material like tiny snowplows. Closer to the planet lies the C ring, which is much fainter and far more transparent, composed of darker, perhaps slightly older or more polluted material. One of the most defining and famous features of the entire ring system is the Cassini division. This is a massive, 4,800-kilometer wide, or 3,000-mile wide gap situated between the A and B rings. While it looks like completely empty space from Earth, it is actually filled with faint, dusty material. The Cassini division is not just a random void. It is a stunning visual representation of complex orbital dynamics in action. The gap is actively maintained by a precise 2-to-1 orbital resonance with the moon Mimas, which is often affectionately called the Death Star moon due to its massive, gaping Herschel crater. Any single ice particle orbiting within the Cassini division takes exactly half the time to orbit Saturn as Mimas does. This mathematical relationship means that every time the tiny ice particle completes 2 orbits, it receives a perfectly timed gravitational tug from Mimas at the exact same location in space. Much like pushing a child on a swing at the exact precise moment to make them go higher and higher, these repeated gravitational kicks drastically alter the particle's orbit, forcing it completely out of the division and leaving a sweeping, remarkably empty lane in the middle of the rings. Beyond these resonances, the rings are also beautifully sculpted by what we call shepherd moons. Tiny satellites like Prometheus and Pandora orbit tightly along the edges of the incredibly narrow F ring. Their combined, competing gravitational influences act just like cosmic sheepdogs, diligently herding the icy ring particles and preventing them from spreading out entirely into space, actively creating intricate, beautiful braided patterns in the flowing ice. Furthermore, the rings are absolutely not a dead, static environment. Data from Cassini indicates that the rings actually possess their own distinct, localized atmosphere. As powerful ultraviolet light from the sun constantly bombards the pure water ice in the rings, it breaks the chemical molecular bonds, releasing molecular oxygen and hydrogen. This process creates a delicate, transient atmosphere that physically clings to the rings, a quiet testament to the continuous chemical evolution happening right now in the freezing vacuum of space. The profound realization that Saturn's rings are young forces us to confront an equally profound, somewhat melancholy truth. They are completely temporary. We, as a species, are incredibly fortunate to exist in a very narrow window of cosmic time, a mere blink of the universe's eye, where Saturn actually possesses its magnificent halo. The rings are currently in a state of rapid, unstoppable decay. The exact same forces of gravity and magnetism that dictate the planet's internal dynamics are slowly but surely tearing the rings apart. This fascinating phenomenon, known as ring rain, was first theorized from old Voyager data and was vividly, undeniably confirmed by Cassini and the Keck Observatory in Hawaii. Saturn is constantly bombarded by ultraviolet radiation from the sun, and the ice particles in the rings are relentlessly colliding with tiny, fast-moving meteoroids. These energetic interactions literally strip electrons from the water ice, turning the once neutral particles into highly electrically charged ions. Once they become charged, these microscopic fragmented pieces of the lost moon Chrysalis are violently caught in Saturn's incredibly powerful magnetic field. The planet's magnetic field lines intersect the ring plane and physically curve downward toward the planet's upper atmosphere. The charged ice grains are pulled fiercely along these invisible magnetic tracks, spiraling quickly out of the rings and plunging directly into Saturn's atmosphere at blistering, hypersonic speeds. As they aggressively hit the upper atmosphere, they instantly vaporize, reacting with Saturn's ionosphere and actively creating glowing bands of infrared light that our astronomers can actually detect from Earth. The sheer volume of material raining down on Saturn is truly staggering to comprehend. Scientists carefully estimate that a massive 10,000 kilograms, roughly 22,000 pounds, of ring material completely falls into the planet every single second. To put that into perspective, that is enough pure water ice to completely fill an Olympic-sized swimming pool in just half an hour. Coupled with the ring material that is naturally falling directly into Saturn's equator, this relentless, unstoppable drain means the rings are absolutely living on borrowed time. Current scientific estimates suggest that the main, visible body of the rings could vanish entirely in as little as 100 million to 300 million years. When the rings finally dissipate into nothingness, Saturn will be left as a bare, slightly tilted gas giant, its absolute grandest feature completely erased by the exact same gravitational and magnetic forces that govern its everyday existence. The story of Saturn, its unusual tilt, and its breathtaking rings is a profound reminder that the cosmos is absolutely not a quiet museum of static exhibits. It is an active, violent, and deeply interconnected engine. For billions of years, a forgotten, icy moon named Chrysalis stood as a silent sentinel, anchoring a massive gas giant in an invisible, ancient tug-of-war with Neptune. But the relentless, creeping outward march of Titan completely rewrote the gravitational rulebook of the entire Saturnian system. The resulting chaotic resonance and the catastrophic, explosive tidal disruption of Chrysalis completely reinvented the planet forever. It freed Saturn to spin at its steep 26.7-degree angle, and it scattered millions upon millions of tons of fresh, bright water ice into orbit, painting the magnificent sweeping rings we marvel at today. As we point our telescopes toward the Lord of the Rings, we are not just looking at a pretty planet in the dark. We are looking at the glittering, shattered remains of a lost world. We are watching the ongoing, dramatic consequences of orbital dynamics, mean motion resonances, and terrifying tidal forces playing out in real time right before our eyes. And as the majestic rings slowly rain down into Saturn's crushing atmosphere, we are profoundly reminded of the fleeting, ephemeral beauty of the universe itself. In the grand, sprawling timeline of the cosmos, Saturn's rings are just a brief, spectacular fireworks display, and we just so happen to be incredibly lucky enough to have a front row seat. Thank you for listening to G Fun Facts Online. Keep looking up, and never stop wondering about the incredible universe we call home.